Okay, now that we've talked about deriving test cases, or at least unit test cases, from our specification that we have developed so far, we're now going to go into another way to derive or come up with actual test cases. Namely, we're going to talk about structural testing. And the key difference here is structural testing is going to be test cases derived from the source code itself, as opposed to what we've done so far as the model and our own experience, what we think would be good test cases. Right, so learning objectives, structural testing, and recognizing all the characteristics thereof. But dialing back, what is structural testing? This is really just judging it from the structure of the program. Very common terms out that I've heard are white box testing versus black box testing. What we've done or talked about so far is black box testing because we're basically deriving from the specification. We're not looking at the code. We're looking at the spec or the way we believe the code should behave. White box is going to be, okay, here's the code. Can there be other test cases you can derive while looking at the code? Now, why are we doing this? Well, why do we do structural? Why isn't functional sufficient? If you think back again, due to the halting problem, we can never really guarantee that our programs are 100% correct, and we also have a very difficult time guaranteeing that all the test cases would come up. We're going to test everything. So structural is going to be another way or another tool that we use in order to decide if our test cases are sufficient for the quality that we wish to achieve for our program. I know it's a mouthful, but that's fortunately the best way to think of it, I've learned so far. So what is structural going to give us? Well, by evaluating the code, we can look at different elements. For example, we can look at control flow, the statements, the branches, and maybe some combinations of conditions or paths. And this is a different view into what our test cases can be as opposed to our previous evaluation, which was based on the spec. And what it comes down to is, since we can't have a program that automatically generates all these test cases, we just need to come up with other ways to look at it and come up with better test cases for our programs. Keep in mind that this complements functional testing, because since we're looking at it differently, it should not produce the same exact test cases, although there'll probably be some overlap. Naturally, we're not going to guarantee that we're going to find all the faults. It's just that the idea is hopefully we'll come up with finding more faults than if we just use black box testing. It's really good at actually removing or coming up with some obvious inadequacies, which we'll see in a bit. Again, it complements functional testing. All right. It really helps with coming and missing up different fault paths that we may not have seen if we were just going with the functional spec. Maybe there's some we didn't know that in the functional spec. Maybe we never said that there's a hash table. But when we look at the code, we say, oh, there is a hash table. Maybe we need to test for collisions as well. That's a pretty good example of why structural testing can be very helpful. In practice, most people create a functional test suite first, and that makes a lot of sense. You want to make sure that your code at least works for what you intend it to do. And then afterwards, once you've come up with a solid design and you've implemented design, now you can start doing analysis on your implemented design and come up with future or further test cases to make sure your implementation is sufficient for the program. Oh, one last thing. This is actually very attractive testing because a lot of it can be automated, as you will see soon. All right, first category of structural testing. Notice that there's going to be many different categories here. The first and most common one is statement testing. Literally going through and making sure you actually execute every single statement. The rationale here is that a fault in a statement can only be revealed if you actually execute the statement. So from your functional test, you run your statement testing criteria, and you find out, oh, wait a minute, we're not executing every statement that's in the program. Well, now you know of another good test case. You can probably come up with another good test case, executing that extra statement for you, and hopefully that will reveal a fault, if one exists, or give you confidence that the code is still working properly. The author likes to make a distinguish here between statements or blocks, aka basic blocks. What it comes down to is difference is only in granularity, namely that if you're using basic blocks or statements, you can group them together because once a test case enters a basic block, it's going to execute all the statements in that basic block. So there's essentially no difference if you have 100% statement coverage, you're going to have 100% basic block coverage and vice versa. Although if you're not quite at 100%, there may be some differences in numbers. But in general, we accept that either way is a good way to evaluate it. You can do it by statements or basic blocks. So here's an example over on the right. You may be looking at the test case. If we were to look through this code, you'd come up with notice that this is a CGI decode, so this is coming in with an encoded URL with that whole, plus %ID adequacy. Plus means a space, and the percent number and digit means some other character, and you're just replacing those with the actual decoded ASCII string. So this would become test space case and whatever %1D is adequacy. Maybe that was a dash or something, I can't remember. So the first one with the plus and a bunch of different letters kind of runs through most of the test cases. The second two come up with other test cases as well, or more statement coverage. What's important to realize here is the coverage does not depend on the number of test cases. You could actually, if you were really crafty and your code was set up a certain way, you could come up with one test case to have full code coverage or statement coverage. Minimizing the test suite is seldom the goal. Once you have your functional test suite, the purpose of statement coverage criterion is to come up with new test cases, not so much to remove your old ones, because your old ones are probably testing some functionality of the code that you want to ensure are working correctly. So the idea here is you don't want to necessarily minimize the test suite for statement coverage. You want to come up with other test cases. Notice that small test cases may make failure diagnosis a lot easier though, so it's something you do want to look into if you can at least combine it structurally. So all statements can miss some. Suppose here block F were missing, statement would not require a false branch from D. All right, take a step back here. I'm going to tell you what this guy's what he's trying to explain here of why just statement coverage is definitely not adequate for structural testing, is what he's trying to prove here, or trying to show you here. If we were to take this piece of code and let's just pretend that this else, dereference of D pointer equals dereference of the encrypted pointer, this piece of code just didn't exist in your code, just for the sake of argument. And then you read this test case. It would actually, if you ran through and looped through all these numbers, it would hit all these different basic blocks, but it would never execute this else. The reason why this is missing something is there's definitely a case that could come up where if C was not a percent, and skipping all this value would come up with some type of error, just for the sake of argument. Even though we're having 100% statement coverage, we're not covering all the different structural paths that could possibly occur in this code. So the statement coverage is not going to adequately cover everything. Well, logically you can see from here that this is based off of a branch, so maybe we should start looking at the branches as well as the statements as well, in addition to the statements. And this is where branch testing comes in. So here we're going to have each branch. This is the edges of your control flow graph, so every true, false, whatever you can branch like that. You want to make sure that each branch is covered. So number of executed branches over branches. So here 100% statement coverage over previous one, but only 88% branch coverage because it missed a branch. Well, if we go and we add that extra test case, then we can get the 100% branch coverage, because we're now taking in fact that missing branch that wasn't in the code, didn't have any statements, but is a branch that does need to be tested. Alright, so traversing all edges causes all nodes to be visited, so test suite that satisfies a branch condition for program also satisfy the statement. Obviously the converse is not true, we just showed that. Just because you have every statement doesn't mean you have every branch, but you have every branch, you have every statement. So you could say that you only wish to look at branches. This is a misnomer, because one thing I haven't touched base on is very few programs in my experience have 100% statement or 100% branch coverage inside of their regression test suites. This is simply due to the pragmatics of testing the program. So you do want to still look at both of these, but do keep in mind that if you end up having 100% branch coverage, you don't need to worry about statement coverage. Although since both these parts are going to be automated with some type of tool, you can just look at both results and be able to move from there. Okay. All branches can still miss some conditions. So now you may think, well, maybe branches will fix all of our structural testing. Fortunately, that's still not the case. Sample fault missing operator, so for example, negation. Alright, so here we have if digit high equals 1 or digit low equals 1. If you look at this from a pure branch statement, we are actually, branch path, you're actually missing a couple of things here. For example, if you want it to be true, all you'd have to do is set digit high equals 1 and then you're done, and that's your true test case. You didn't have to test the case in branch coverage of digit high being 0 and digit low being -1. Digit low, yeah, -1. So there might be other paths to the condition testing that need to be tested. Namely, we need to make sure that this conditional on the right is actually tested correctly. And this goes into condition testing, where you go into testing different parts. So branch coverage exposes faults on how computation can be decomposed into the different cases. This is nice and intuitive, but only roughly. Condition considers case analysis in more detail, individual ones. Both parts of digit high equals 1 and digit low equals -1. As I just gave you an example previous, if you're just testing for a branch of true, you'd have digit high equals 1, and then false would be both of these were false. You never test for the true test case of digit high being maybe 0 and digit low being -1. So in this case, basic condition, coverage, all the truth values taken by condition, then 2 times number of basic conditions. Hopefully you can see that this is actually going to get a little bigger. Basic condition adequacy can be satisfied without the branch coverage. So this is a little hard to see of how this is the case. But if you go back and you run through the examples, you'll see how I believe this path always never goes along the else. Yeah. So what it comes down to is branch and the condition are not comparable. They don't imply each other. In a way, this is good because this means you can now look at your structural code from 2 different perspectives and maybe come up with some better test cases, as opposed to just one subsumes the other. Okay, so how do we test this? You want to first make sure you cover all conditions and all decisions. For example, if digit high is -1 is false, then you're always going to get false. But if it's true, then digit 1 being 1 would still make the statement true, otherwise it was false. You'd jump back to false here? Oh, this picture is backwards. These 2 statements need to be brought up. All right, let's go look at compound complexity so this will make a little more sense. I'll get back to this in a moment, guys. Exponential complexity. Notice here we have 4 different values. Well, how many different ways can we go about it? Well, A is true, would make this whole true, and then B is irrelevant. Then you need C to be true, and then you have to have E equals true. If you actually go through the different test cases, about 13. Short circuit evaluation can reduce it to a more manageable number, but not always. Keep in mind that if you were to test these out, we have 5 variables up to 13, and if every time you add a variable, this number of test cases can grow, namely exponentially. It could double potentially each time. If it was just a bunch of ors, it would double every time you added another variable. So it can become exponentially complex to try and do condition testing inside of branches. So what do we come up with? Or what do people come up with to try and resolve this? It's called the modified condition decision. The idea here is instead of having to deal with all the exponential different paths here, we're going to try and simplify it. We're only looking at important combinations. For each basic block C, the 2 test cases evaluate conditions except C are the same. All right, this makes more sense if there's an example. Here we go. The idea is, let's see if we can take these 13, which ones are actually important? Well, if A is true, C is true, and E is true, then we don't really care about B or D, so we can actually eliminate any of those test cases there, and they're true. On the other hand, if A happens to be false, B is true, the rest is true, we're still good. Notice that in the first 3, we're going to test that these three values are true. Remember, underlying values independently affect the output decision. Okay, this is actually a standard. But the point here is now we've affected these three are true, we're good. Let's just change one of them, namely B. All right. Now let's change a different one, namely C. All right. Now let's change the sixth one, false. All right, we're good. Now, what else can we do to change it? Well, let's just change two other variables, C and D, and let's change the last two variables, B and D. If you notice that we're looking at it from a how can we change a single variable to eliminate some of the additional overlap. If you were to go back and you evaluate it, it's still going to be basic condition coverage because you are testing essentially the different paths of short circuiting. You're just skipping some test cases that overlap each other. And there's one additional one because they must independently affect the decision's output, because you're ensuring that just changing one is going to change, for example, changing the A is going to change this one statement, which trickles down essentially and changes the rest. Now we just need to evaluate if this is true or false for everything. We don't need to move on. Same thing with the adding C. We're just evaluating if this whole condition is true or false after we evaluate if this is true and if the C is true or false. So it's just a way to help simplify it. Sorry. It is subsumed by the compound conditions, right? So it's stronger than compound and branch coverage in a way. And this is a good way to do at least the condition testing. All right. Lastly, we want to talk about paths. Should we explore sequence of branches in the control flow? Fortunately, if you think about this, there are many more paths than branches, because now each decision will affect every new decision afterwards. Can be pretty complicated. And in fact, well, if you actually think of applying the path adequacy here, you want the number of executed paths over the number of paths. But the question here is, how many total paths are there in a program? Well, if you have a loop, then there are a lot of paths, because the loop, how many times can a loop execute? Well, if you're looking at it from a theoretic standpoint, it can go ad infinitum, which makes it basically impossible to try and satisfy this criteria. So we have to at least make it feasible, and we usually do that by taking your loops and partitioning them into the useful test cases that we think about. One where there's a number of traversals in the loop, maybe 100 or 10. Make sure we actually, the paths are, number of traversals of loops. Maybe we'll limit the number of paths in our path criterion, and maybe we'll have to look at the dependencies among the different paths we've selected. So this is actually an exponential problem that we're trying to simplify pragmatically. All right, bounded interior path, right. So you want to group together paths that differ only in the subpath they follow. Basically, if you can merge a bunch of paths into one super path where the subpaths maybe differ only slightly, that way you can only test the couple of different subpaths, and then you can move on from there. Let's see. Yeah, if you notice here for the different loops, B could go from B from right here. Well, since they're all going to be here, let's just simplify them and just move them back up, and that way we can simplify this as just one long path if we wanted to. Alright, they're just trying to show you here, in case it wasn't clear earlier, that everything can go exponentially. For example, if you have if A, S1, if B, S2, if C, S3, etc., etc., etc. Since you could either take the if or not take the if, every time you add another one of these, the number of paths increases by a factor of 2, which makes it exponential and hard to, or pragmatically impossible, to generate all the test cases for. So when you're doing loop boundary adequacy, I almost went into this for the slide, but the point is you want to simplify it. One test case, the body's iterated 0 times, the body's iterated once, and then more than once. So 0, 1, 100, 1,000, whatever you would think a common case is. And then you just limit your path to just those 3 things. This should be somewhat intuitive because you're testing the 2 corner cases of 0 and 1, and then of course all your normal test cases of multiple times. Alright, linear code sequence and jumps. This can be a little hard to understand at first, what they're talking about. Sequential subpaths in the CFG starting and ending in a branch. All right. So this is not a basic block. Well, it could be a basic block, or it could be multiple basic blocks. But the idea is that sequence starting and ending in a branch. So you could combine a bunch of basic blocks together until you had one branch coming in and then one branch coming out. So these LCSAJs, linear code sequence and jumps, could be a basic block or multiple basic blocks grouped together in some sequence where there's one in and one out. Fortunately, that's all that these slides give you. Hopefully that makes some sense. You could think of it as a super block if that helps, instead of just a basic block. All right, then we got, let's see, cyclomatic adequacy, number of paths of independent paths in the CFG. All right, so this is the total number of paths that we could have. Basically, it counts the number of independent paths that have been exercised relative to its actual complexity. All right, I'm not going to go into this too much. All right, so far we've talked about, let's see, statement coverage, branch coverage, conditional testing, and then of course path testing as well. If you think about those pieces of code, we're usually thinking of them inside of a function. What comes next is, now that you can do the analysis inside of a function, you want to look into procedural call testing. This has historically been very difficult because of how you can jump from one function to another, and that could go almost anywhere in the code and affect the state of actually affect the general state of your program, which could affect again differently how your program's called. So this type of analysis can get very complex very quickly. But afterwards, at some point, you want to look at least procedural call testing. A lot of people don't get into this too much because of how complicated it gets, but this is more gearing towards a system testing or integration testing, because we've already done unit testing that usually tests single units of code or functions pretty well, but now you want to look at how can one procedural call affect another procedural call. And this is usually called call coverage. May have multiple exit and entry points, because you can exit a function at many different points. So you can do a return. All right. The book doesn't go into this too much because, well, hopefully it doesn't, because it is pretty complicated. But you can look at call coverage. Most of the tools I've gone out and reviewed pretty much stick with branch, statement and branch coverage. I haven't seen too many on conditional coverage, although I would love to see something that come out with that. All right, the subsumption relationship. So look at the bottom. In other words, if you have statement testing, all right, that's nice. If you have branch testing, that subsumes statement testing, aka your branch testing at 100%, your statements will be executed at 100%. You have your linear code jumps, it'll subsume the bottom. Notice that branch and condition testing, of course, is going to take care of branch because it's branch and condition combined. MCDC actually subsumes both branch and basic, and then compound testing. Well, this goes from the practical criteria to theoretical. What this picture's trying to tell you is, down here, easiest, but doesn't give you too much, gets more and more hard, it gets harder and harder, until you actually get into something that's more theoretical, and we don't have too many tools that'll help us out there. Notice path testing's at the top. I haven't seen too many tools to do that. All right. Satisfying structural criteria, a lot of times it may not be satisfiable. Pretty much once your program becomes sufficiently large, I can tell you it's just not going to happen. But that doesn't mean this isn't useful. It can still give you a lot of important information. And in your project, part of your job is to actually show that the number of statements executed and the number of branches executed has increased with your code. So you'll have to go and look at some pragmatic tools that will generate a graph showing you that from your test cases that you've derived. So it requires execution of statements, all right, that can be executed, usually conditions, and then paths, although paths are a little harder to have a program generate a report on. This is actually, well, they call it fossil code here, aka leftover code, may indicate maintainability problems. If a code isn't reachable flat out, well, then that might actually tell you to eliminate some code, which would help in the long run of the health of your code base. In general, most people set code coverage to less than 100%. Usually debates between 80 and 90% depending on your project. It could be lower depending on really what you're working on. Of course, if you're working on a medical equipment that's going to keep someone alive, you're probably going to be pretty much 100%. And you can look at these two standards if you feel so inclined, but I'm not going to cover them in this course. All right. So we define adequacy criteria. Remember, these criteria are not design techniques. They're just to give us feedback about our test cases from a structural standpoint. The different criteria address different problems, structural branch condition, etc. And when table inverse is usually really hard, how to find a program input allowing to cover something buried deep in the CFG, you probably have to go and look for it. This is why most people don't require full adequacy, they some degree of it by code coverage measuring techniques. And that's why most tools actually report both statement coverage and branch coverage, because you remember those two numbers may be different. All right, that's it for chapter 12.